Managing an integrated steel plant is definitely not an easy task. You constantly have to deal with decisions, such as, which materials should you purchase? There are so many suppliers offering different prices and qualities. Which qualities should you produce? Each one having its own cost and throughput. What is the best production level for each unit? How should you balance the production cost with the price of alternative materials? How should you operate each process? For instance, what is the best coking time or the best hot metal temperature to target? Or how can you justify an investment to debottleneck specific equipment? And as if this weren't enough, you constantly have to interact with and convince many people while taking into account their different expertise and points of view. You have to track new market conditions, such as price indexes or availabilities, and be ready to quickly make new decisions when unplanned events occur. That is why we at Cassotis Consulting developed a mathematical model, a method and a tool to help you make all these decisions and select the most profitable choices. Your solution will be custom-made to faithfully represent your integrated steel plant and its specific technologies and processes. The main objective of the model is to maximize the overall profit. It considers all the costs and revenues from both products and byproducts. That is why we will make a case-by-case analysis to carefully determine the fixed and the variable part of each economical aspect of your business. The capacity of production of each unit is impacted by operational conditions, as well as the targeted quality and the type of charge. The model investigates various levels of production for each unit that are all consistent with the reality of the process. Every process step has to respect the basic principles of physics, such as mass and chemical balances. As a matter of fact, the model considers all possible material flows based on their physical and chemical characteristics. The key aspect of the model is its end-to-end integration for decision-making. Even if your process is very complex with many interrelated flows, the model does not look at individual departments separately. It considers the whole process at once to evaluate the impact of each single decision. The model also challenges the specifications for intermediate products depending on your plant's operating conditions. For example, the sulfur content in the coke combined with the desulfurization strategy at each production step should depend on the price of high sulfur coals and the cost of removing the sulfur, an extremely complex balance whose key operational choices occur at both ends of the steelmaking process. The overall energy balance is guaranteed and is impacted by any decision in the reduction and conversion processes. The distribution and the proportion of gas to produce electricity at the power plant considers the generation of gases from the processes and their cash costs, the consumption of gases by the processes determined by their energy balance, and the purchase of natural gas with its market price. The same balance applies to the electricity between production, consumption, and purchase. Environment is an important part of the decisions nowadays. With this model, you can easily estimate the emission of gases impacted by the operations and choice of materials. As a result, you can decide whether you restrict or penalize concentrations and volumes of pollutants according to the environmental regulation. We are not presenting here 6 models, but a unique model that integrates all those aspects at once, because any decision regarding one will impact the others. And you may ask how we model each of these submodels. Each of them is based on a set of equations that represents the real-life process. The first 2 are based on microeconomics theory and the laws of physics. The cost calculations, which are derived from the consumption and revenues based on the actual sales, constitute the economic part of the model. The resulting profit is directly related to the objective function of the optimization. Any universal laws of physics, such as mass balances, are modeled in their pure theoretical form. The rest of the equations for the remaining 4 aspects are usually based on regressions, derived from your plant's actual production data. If appropriate, variables are combined in a nonlinear form, so the solution can handle such a complexity. This approach makes the solution, custom-made for your plant, consistent with the reality of your process, and ready for making integrated decisions for your steel plant as a whole. So let's go back to our integrated steel plant and see how these concepts can be applied. With the model, you can be sure that any decision has been globally optimized and analyzed with quantitative criteria, always seeking the highest profit for the company. The procurement of material will be based on global quality and cost trade-off. The resulting blends will be optimized and consistent with your production targets. The order book will give preference to the most profitable products. The overall production level will be the one that best matches your production with market demand, avoiding overproducing at negative margin profit. The operating setup of your plant will globally reduce your costs by 1 to 5 USD per ton. Calculate the return on your investments to back up your business case. And finally, use this solution to align all stakeholders on a common and unique objective. Procurement and process experts working together for the negotiation of best selection of raw materials. Sales and process experts determining together the right production levels and the right price to market a specific product. One unit manager agreeing to produce at a higher cost because the gain in the subsequent process step is bigger. And many, many more. This model applies to many other industrial processes as well. Interested? Enter in contact.